Today we are going to discuss about molecular orbital theory. In the previous lectures, I discussed the Lewis theory, the valency shell electron pair repulsion theory or Vesper theory, the valency bond theory. While the Lewis theory and Vesper theory are classical theories, both valence bond theory and molecular orbital theory are quantum mechanical theories. So these two theories consider electron as a wave. So we can associate a wave function with electron. This wave function is termed as orbital. So we use this orbital concept both in valency bond theory and in molecular orbital theory. While in valence bond theory, we discuss atomic orbitals and hybrid orbitals. In molecular orbital theory, we say that atomic orbitals combine to form molecular orbitals. So we'll discuss the main ideas of molecular orbital theory now. This theory was proposed by Hyundai and Milken in 1950s. According to this theory, atomic orbitals on atoms combine to form molecular orbitals. So we can have two kinds of combination. The positive lobe of one orbital can overlap with the positive lobe of another orbital. So this results in a constructive interference resulting in increased electron density along the line joining the two nuclei. Here the electron density is increased. So this increased electron density is responsible for the bonding in the molecule. So this kind of orbital is called bonding molecular orbital. If positive lobe of one orbital overlaps with negative lobe of another orbital, this results in destructive interference and there is no electron density in this region, in the region shown. So in between the nuclei, there is a zero electron density due to destructive interference between the orbitals. Such orbital is called anti-bonding molecular orbital as electron density is reduced between the two nuclei. Further, we can classify the orbitals into sigma molecular orbitals and pi molecular orbitals. As we have just seen, if two s orbitals combine, we can have only sigma molecular orbitals, sigma bonding as well as sigma anti-bonding, that is sigma star molecular orbitals. But if we consider two p orbitals, if there is sidewise overlap, like shown on the right hand side, then we can have pi molecular orbitals. So we can have two kinds of overlap. In phase overlap, that is the positive lobe of one overlaps with positive lobe of another. Here we have a pi bonding molecular orbital. If positive lobe of one orbital overlaps with negative lobe of another orbital, then we get a pi anti-bonding molecular orbital. P orbitals can form two kinds of molecular orbitals, both sigma molecular orbitals as well as pi molecular orbitals, whereas s orbitals can form only sigma molecular orbitals.
So electrons are filled in molecular orbitals following certain rules. So these are Aufbau principle, Kunz rule, and Pauli's exclusion principle, which are the rules that we usually apply when we fill atomic orbitals. So the same rules, Aufbau principle, Kunz rule, and Pauli's exclusion principle, also apply for filling electrons in molecular orbitals. So what is Aufbau principle? So when electrons occupy molecular orbitals, they occupy in the order of their increasing energies. That is, the lowest energy orbital is occupied first, and then the higher energy orbitals will be occupied. So in the case of boron, carbon, and nitrogen, the orbital energies follow the order. Sigma 1s is lowest in energy, then the sigma star 1s, which is the anti-bonding molecular orbital. Then we have sigma 2s, which has lesser energy than sigma star 2s. Then pi 2px and pi 2py, the two pi orbitals, they are equal energy, they are degenerate. And then the sigma 2pz orbital, followed by the two anti-bonding orbitals, pi star 2px and pi star 2py, which are again degenerate, they have the same energy. And finally, the sigma star 2pz anti-bonding orbital. So please note that in case of boron, carbon, and nitrogen, we have pi 2px and pi 2py have smaller energy than sigma 2pz. Whereas in the case of oxygen and other heavier elements, the sigma 2pz is smaller in energy, so it is filled first, and then the pi to px and pi to py orbitals will be filled. So in this way, we have to fill the orbitals. First, the lower energy orbitals are filled, and then the higher energy molecular orbitals. Going to Hund's rule, when there are two degenerate orbitals, for example, if we take pi to px and pi to py, when we are filling degenerate orbitals, if we have two electrons, first we should make sure that we have maximum number of unpaired spins. That means we should fill one electron each. We should not fill both the electrons in the same orbital. Instead, we should fill it one electron each. So the first electron will be in pi to px and second electron will be in pi to py, because this will maximize the number of unpaired spins. So this configuration will be more stable than the configuration in which the two electrons occupy the same state. So Hund's rule says that electrons occupy degenerate orbitals in a way as to maximize the number of unpaired electrons. So when there are two electrons, one electron in pi to px and the other electron in pi to py. And finally, the Pauli's exclusion principle, which says that no two electrons can be in the same quantum state. Let us take two electrons. For example, if one electron occupies pi to px with spin up direction, we cannot put another electron into pi to px with the same spin. If we want to put the electron, one more electron in pi to px, we have to put it with opposite spin. Then the quantum state will be different. One quantum state is pi to px with clockwise spin, and other quantum state is pi to px with anti-clockwise spin. So while filling molecular orbitals, we have to keep these three principles in mind: Aufbau principle, Hund's rule, and Pauli's exclusion principle.
So let us consider the molecular orbital diagram for hydrogen molecule. Here we have two hydrogen atoms, 1s orbital on one hydrogen atom and the 1s orbital on the other hydrogen atom. These two combine to form two molecular orbitals, sigma 1s, which is a bonding molecular orbital, sigma star 1s, which is an anti-bonding molecular orbital. So the two electrons are occupying the bonding molecular orbital, which explains the bonding in hydrogen molecule. The total bond order of the system can be calculated as number of bonding electrons minus number of anti-bonding electrons divided by 2. So here we have two bonding electrons in the sigma molecular orbital, and the sigma anti-bonding molecular orbital is empty. So we have 2 minus 0 by 2. So total bond order is 1. So there is only one bond between the two hydrogen atoms. So this is the molecular orbital representation for hydrogen molecule. Now let us take the example of a nitrogen molecule. So here we have two nitrogen atoms. The electronic configuration of nitrogen is 1s2, 2s2 and 2p3. So just ignore the 1s orbitals for the time being, and here I show only 2s orbitals and 2p atomic orbitals. In the 2s orbitals we have 2 electrons, and then the 2p orbitals we have 3 electrons. And same is the case with other nitrogen atom. So the 2s orbitals on the two nitrogen atoms combine to form sigma 2s bonding orbital and sigma star 2s, which is a anti-bonding molecular orbital. So the 4 electrons are filled in this sigma 2s as well as sigma star 2s. Similarly, the p orbitals combine to give both sigma 2p orbitals and pi 2p orbitals. Here, in the case of nitrogen, the pi 2p orbitals are lower in energy than sigma 2p orbitals. So we have total 6 electrons. The two pi 2p molecular orbitals, they are degenerate. So the pi 2px and the pi 2py both are occupied each with 2 electrons. And after that, we have 2 more electrons remaining. So these 2 electrons occupy the sigma 2pz. These 2 electrons occupy the sigma 2pz molecular orbital. So the overall molecular orbital configuration is sigma 1s2, sigma star 1s2. So the 1s sigma orbitals are fully filled, and then the sigma 2s and sigma star 2s orbitals are also filled. So here we have total 8 electrons up to here. And then the pi 2px orbital and the pi 2py orbitals are also completely filled. So 2 plus 2 again, 4 and plus 8, 12 electrons are filled. And finally, the sigma 2p has 2 more electrons. So total 14 electrons are there. So these are filled in this manner. To calculate the bond order, we take the number of bonding electrons. So we count the bonding electrons, sigma 1s2, 2 electrons, sigma 2s2, another 2 electrons, pi 2px2, pi 2py2, 4 electrons, sigma 2pz2. So total 6 plus 4, 10 electrons are there in bonding molecular orbitals. Whereas in the case of anti-bonding molecular orbitals, we have 4 electrons. So 10 minus 4, 6 by 2. So the bond order is 3. So we have triple bond in nitrogen molecule between the 2 nitrogen atoms. So this explains the bonding in nitrogen molecule. Now let us go to the molecular orbital diagram for oxygen molecule. So here again, here I am not showing the sigma 1s and sigma star 1s orbitals, but only showing the 2s and 2p orbitals. So as usual, the sigma 2s orbitals and sigma star 2s orbitals are fully filled, and then the 2px, 2py and 2pz atomic orbitals on each oxygen atom combine to give sigma 2pz, pi 2py and pi 2px, pi star 2px and pi star 2py, and finally sigma star 2pz. And then in the 2p shell, we have total 4 electrons. So sigma in 2px we have 2 electrons, 2py and 2pz, each is half filled. So here we have 4 electrons on each oxygen atom and a total of 8 electrons. The bonding molecular orbital sigma 2pz is completely filled with 2 electrons, and pi 2px and pi 2py are also completely filled. So we have 4 plus 2, 6 electrons are there, and then 2 more electrons. So these 2 electrons, one each in pi star 2py and pi star 2px. This is because these 2 orbitals are degenerate, so we can't fill both the electrons in the same orbital, but we have to fill 1 electron each. So as a result, we have this molecular orbital configuration: sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, and then pi 2px2, pi 2py2, and in the pi star orbitals are only half filled. So this, due to this unpaired electron, oxygen molecule is paramagnetic. The bond order can be calculated as number of bonding electrons minus number of anti-bonding electrons by 2. So here we count the bonding electrons: 2 in 1s, sigma 1s, 2 in sigma 2s, 4, sigma 2pz 2, 6, and pi 2px and pi 2py, 2 plus 2, 4. So 6 plus 4, 10 bonding electrons are there, and in anti-bonding molecular orbitals, 2, 3, 1 each in pi 2px and pi 2py, 4, and we have sigma star 2s, 2 more. So we have total 6 electrons. 10 minus 6 by 2. So here the bond order is 2. So we have a double bonding in oxygen molecule. So one important difference between the oxygen molecular orbital diagram and nitrogen molecular orbital diagram is that in the case of nitrogen, the pi 2p orbitals are smaller in energy than sigma 2pz orbital. So they are filled first. The pi orbitals are filled first. However, in the case of oxygen and other heavier molecules than oxygen, sigma 2pz is lower in energy than pi 2px and pi 2py. Therefore, sigma 2pz is filled first, followed by pi 2px and pi 2py orbitals.